We're going to talk about linear transformations, multiplication by a matrix A. We can view this as a transformation. It takes one vector X and transforms it, or maps it, or sends it to a new vector B. So we just think of this like a function. A matrix takes a vector from one space and sends it to a vector in another space, just like a vector takes an X as an input and sends it to a Y. Okay, so if A is the matrix 1, 2, 0, 0, 4, 0, and we're going to define T to be the transformation that takes X as an input and outputs AX. So this is a notation that your book uses a lot. It means T of X equals AX, right? This is the function notation you're more used to. So in your head, you can just do a quick translation whenever you see this. X, arrow, AX. That means X is the input, AX is the output. This is the notation you're more used to. All right, so is T a linear transformation? From the reading, the answer is yes, because every matrix transformation is a linear transformation. Every matrix transformation is linear. So the domain of T. T is my transformation. What kind of inputs can I put into T? So remember, T of X is the matrix A times X. So your inputs are the things that you can multiply A by. So let's think of what are the dimensions of A? 2 by 3, right? So if I'm going to multiply A by a vector, what does its dimensions have to be? 3 by whatever in order to be able to multiply them, but if it's a vector, then it's 3 by 1. Yeah. How do we know that X is a vector and not a matrix? It's bolded. Yeah, it's bolded in the question. So we know that the domain is all 3 entry vectors. What do we call the set of all 3 entry vectors? R3. Codomain is the outputs. Okay, so codomain it's like the range, but it's bigger than the range. Okay, so what kind, if you multiply a 2 by 3 matrix by a 3 by 1 vector, what are the outputs going to look like? What are their dimensions going to be? 2 by 1, right? The outer dimensions. So if you do a 2 by 3 times a 3 by 1, inner dimensions match, so we can multiply them. The outer dimensions will be the result. So the codomain is just the space that the outputs live in, which would be where? 2 by 1 matrix, which is R2. Yeah. Now, I didn't ask for the range, right? Because you can't necessarily create every vector in R2 by multiplying vectors in R3 by that matrix. So the range is some subspace of R2, possibly all of R2, but definitely within R2. So no, this is the codomain. We say it's all of R2. The codomain is slightly different definition than the range. If I asked you for the range, you would not say all of R2, unless you were sure that that was the case. But the codomain is just the space where the range lives. So you can say R2 is the codomain. All right, so what is the image of X being the 3 by 1 vector 1, 1, 0 under the mapping T? So that's just saying, what is T of 1, 1, 0 if I use this notation? T of 1, 1, 0 just means A 1, 0, 2, 4, 0, 0 times 1, 1, 0. And we have 2 methods that you learned a couple sections ago about how to multiply a matrix times a vector. I'm going to go with the like rotate the row, lay it on top of the vector, and the stuff that lines up you multiply, and then you add up all the 3 terms. So you're going to have 1 times 1 plus 2 times 1 plus 0 times 0. And then you go to your next row and multiply that times your vector. So you have 0 times 1 plus 4 times 1 plus 0 times 0. So this is my 2 by 1 vector, which we were expecting, a 2-entry vector. And I get 3, 4. Is there any other vector other than 1, 1, 0 that would give me 3, 4 as an output or an image? Is there any other vector other than 1, 1, 0 that you could use to get 3, 4 as an output? Same original A, yep. So I'm asking for an x1, x2, x3, right? So I could say, let's just write down in symbols what this question is asking. I could say, okay, well, I'm looking for, I have a matrix 1, 0, 2, 4, 0, 0. I'm looking for a 3-entry vector, x1, x2, x3, that when I multiply the matrix by it, I get 3, 4. Yeah, yeah. X3 could be anything. If you study the calculations we did in the first one, you might be able to say, yeah, 1, 1, anything will give you 3, 4. If you didn't see that, you could just set this up and say, this is what I'm looking for. How would you solve this matrix equation? Just make it an augmented matrix and row reduce. So I would do 1, 0, 2, 4, 0, 0, augment with 3, 4. And you get 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 1. So this says x1 is 1. It says x2 is 1. And what does it not say? X3. X3 is in the third column. There's no pivot there, which means x3 is free. Right? So yeah, there are lots of vectors. 1, 1, anything will give you an image of 3, 4. So 1, 1, anything. All right, what if I want to find a vector whose image is 1, 1 rather than 3, 4? What do I do? We're going to do the exact same thing. Instead of 3, 4, I'm going to put a 1, 1, see if I can find an x1, x2, x3 that gives me 1, 1 as an output. So I have 1, 0, 2, 4, 0, 0, 1, 1 this time. That row reduces to 1, 0, 0, 1, 0, 0, and the augment is 1/2, 1/4. Okay, so this says x1 is 1/2, x2 is 1/4, and x3 free. Because again, there's no pivot in the x3 column, so x3 is free. So sure, I could come up with a vector, 1/2, 1/4, anything, right? It's just a little asterisk that your book uses that notation to mean anything. Okay. So that vector, any vector that looks like that would have its image as 1, 1. Is 8, 12 in the range? That means is 8, 12 a possible output of multiplying your matrix by a 3 by 1 vector? Is 8, 12 producible? Yeah, you should do the exact same thing. Same question as before. So I'm just going to 1, 0, 2, 4, 0, 0, 8, 12. It's just an alternate way of asking. Can you produce 812 as an image? Can you produce 812 as an output? Is the same thing as saying, is 812 in the range? So this is 1 0 0 1 0 0 2 3. So the answer is yes. What is the range of T? Okay, so we talked about the codomain because we know all the outputs live in R2. All the outputs will definitely be 2 by 1 vectors. But can you get every 2 by 1 vector as an output? Is there some way to create every 2 by 1 vector? Sure, we could put dummy variables like B1. We could put like B1, B2 here instead of 812. Yeah. So let's, if I did that, I would have 1 0 2 4 0 0 B1, B2. Every time I row reduce to this thing, the left comes out to 1 0 0 1 0 0. And then I'm going to have some stuff here with B's in it. Is this going to be a consistent system?
How do you know it's always going to be the 0, 0, 0, 0?
Oh, good question. So I've done this 3 times now, right? And every time I row reduced this, the left always came out the same.
Okay.
So yes, it spans R2, which means the range is all of R2. Yeah. Each row has a pivot. Range is R2 because each row has a pivot. Okay, so no matter what I put in, no matter what 2-entry vector I want to find out, is it in the range, the answer will always be yes, because the system will always be consistent with a pivot in every row. That's it for the demo. So I believe that this is kind of a longer, yeah, definitely, this is kind of a longer activity. So we still have a little over 20 minutes left. So let's get started on it and we'll finish it up next class.